everyone. Welcome back to another video with Mohammed and I. Today's topic is we'll be talking about what is a switch in networks and the role they play in the local area network or the LAN. So first of all, let's start off with what is a switch. By definition, it is a layer 2 or data link layer if you're looking at the OSI model, networking device that connects multiple devices within a local area network. It operates by learning storage and forwarding frames based on MAC addresses, and it creates separate collision domains for each port while maintaining a single broadcast domain. Multiple port devices. So what this means is it's able to serve 24, 48, 16, depending on your switch size. In a traditional network, you'll see a switch serving your users, right? Your servers, your endpoints. So you need a lot of ports for that. It is a full duplex communication on each port, and we'll go as to what this means. It is hardware-based forwarding, so it uses ASICs or application-specific integrated circuits to forward that data, and it's store and forward or cut through switching methods. So everything that you see highlighted in this slide is the topics that we'll be covering with Mohammed today and go into detail. So Mohammed, do you want to explain to us first, there's a difference between a switch, hub, and a router.
Yep. So we did cover switch in the slide before, which is a layer 2 device, but we also have hubs which operate on physical layer, which is the layer 1 in the OSI model. But the main difference between a hub and a switch, we will say, is the collision domain. All the ports on a hub is one collision domain compared to like a switch, where each port has a collision domain. And a hub and the switch, the main difference you can say is a hub sends the traffic through all the ports. It just takes from one port and sends to every single other port. But a switch is different, where the traffic is limited to that single port. And then we can see other information like broadcast domain, which is single on the hub and the switch, but on the router you can have multiple domains, and that domain just means multiple networks you can have. And also the duplex, the hub only supports half duplex. Meanwhile, the switch and the router, they also support full duplex. And intelligence-wise, hub is dumb. It just repeats the traffic. That's why it's on layer 1. Meanwhile, a switch, it operates on layer 2, so it uses MAC address learning to like transfer the traffic. Meanwhile, router is more intelligent and uses routing protocols to route traffic. So it will take you from your home to internet. Meanwhile, the switch will keep you to your home. We can move forward.
Yeah. So Mohammed, I think this is a term that we're going to see a lot when we talk about switches, which is a duplex,
Yeah.
and what is a full duplex and a half duplex. So I think it's best we probably get that term out of the way for the viewers watching this that maybe struggle to understand that. A duplex, the way I like to think of it, is a lane on a highway. So
Right.
in a half duplex switch, because sometimes you'll see your switch negotiates to that, not, and then you have to manually configure it to do full duplex. But what a half duplex is, imagine a single lane on a highway that's passing traffic bidirectionally. So what that means, you'll have inbound traffic and outbound traffic crashing and just dropping the packets. And what that does is, once you have those collisions, you are essentially just dropping inbound and outbound traffic repeatedly. So you have to stop forwarding frames when you are receiving frames. You have to stop receiving frames when you are egressing frames, and so
Right.
on. So what a full duplex is, it is a two-lane highway that creates two separate lanes, one for your egress traffic, one for your inbound traffic. And egress means outgoing traffic. So your inbound traffic is coming in one lane, your outbound traffic is coming in another lane, and they'll never see each other and intervene with each other. When we are talking about bandwidth, so you'll see 100 megs or a gig on a switch port. What that means, it is 100 megs outgoing and 100 megs incoming because it is full duplex.
Right.
So moving on to the next slide, we'll talk about MAC address table or a CAM table. It is a content addressable memory, which is a hardware-based lookup table stored in high-speed memory. It maps MAC addresses to physical switch ports. And that is the most important thing to remember on this slide, or what a CAM table is. It is that a MAC address table is a mapping on a switch that says, anytime I need to reach this MAC address, it lives on this switchboard. So it enables efficient frame forwarding decisions because it's stored, and every time a frame comes in, it's able to compute and say, okay, the egressing port for this MAC address is here. So essentially, the table structure looks at something like this on a Cisco switch. It is very vendor dependent. You'll see that the theory is the same on every networking switch, but you'll see the output being different on a Cisco, Juniper, Brocade switch, whatever you're using. But essentially, it mentions the MAC address of the endpoint, the port that it resides on, and the VLAN at which the MAC address is being learned. Then the age. You'll see that the key parameters at the bottom, there's an aging time at default of 300 seconds or 5 minutes. So this is the time to expire. Anytime an endpoint is forwarding frames or sending frames to the switch, it resets that timer. So if an endpoint is communicating constantly, you'll see that the age is continuously resetting. But if a device stops talking on the network, the age will just be none and be deleted off the MAC address table. So then the table size varies depending on the switch model. Some switches can only support 4,000 MAC addresses, and others support up to 128,000 entries. The learning method for this is dynamic learning through source MAC inspection. So, and we'll go into the lab portion of this later, but you'll see that on the switch itself, it'll tell you the learning mechanism it used, and you'll see dynamic more often than not because that's how the switch interprets the endpoints. Next slide.
Okay, so how does the MAC address learning process go? So step by step, frame reception. So a switch receives a frame on a port. In this diagram, we can say that the PC0 is sending traffic to PC1. So the switch will receive traffic coming from PC0 on the port. That's how it will learn its source MAC address. So source MAC examination, it will extract the source MAC address from the frame header. So layer 2 has a frame header in which you will define the source as well as the destination MAC address. We'll cover more OSI model and different layers in a later video so that it makes more sense from the OSI layers perspective. The table lookup, so it will check if the MAC address exists in the CAM table. So it will see that the destination MAC address, or first of all, does the source MAC address exist in the CAM table? If it does not, then it will add an entry in the CAM table for the source MAC address and also the port it received that source address from. So it will associate the PC0 and its MAC address ABAE with the port that the PC0 is connected to on the switch. And the CAM table will populate with that information with, again, the default timer of, let's say, 300 seconds, which is on most switches. Next, it will make the learning decision. Again, if it's a new, then it will add a MAC to port mapping, which I just described. If it's existing on the same port, then it will reset the aging timer, the 300 seconds default timer. And if it exists on a different port, then it will update the port mapping. So let's say that PC0 connects to the switch, or it's a laptop and you connect it to another port on the same switch. It's going to update the CAM table with the new information of that source address and the new port that it connected to. Now, learning states-wise, you have unicast, unknown unicast. If the destination MAC address is not in the CAM table, so source MAC address, you already know that it's associated with the specific port. In this example, we can say fast Ethernet 0/1. But the destination MAC address, you do not know where or which port the destination MAC address is at. Then the switch will flood the frame on all the ports that it has. And the PC that has that address will send back to the switch that, hey, it's me. And that's how it will populate the information about the destination PC or whatever device you're using. If it's a non-unicast, then that means that the MAC address is already in the table. So the destination MAC address is already in the table. So it will just send the traffic directly to that port or that device. And
Yeah.
the MAC aging, as the timer expires, if the communication is not there between the devices, or the PC0 is not communicating to any other device, then the MAC address table, the aging timer will expire and the entry will be removed from the CAM table. I think that explains the MAC address learning process.
Yeah, yeah, that's right on the dot. So when we talk about the freight forwarding methods that a switch has, there's a stored and forward, which essentially the switch receives the entire frame before forwarding that data, and then it performs error checking or FCS validation. Basically, it'll verify that all the frames are in line before forwarding it. And the thing, if you're checking that entire frame, it'll create higher latency, but it essentially guarantees an error-free transmission, and it is the most common method in modern switches today. Um, then you have the cut through, which essentially forwards the frames after reading the destination MAC address. If you look at what is a packet or what is a frame containing the actual content of it, you'll see that in the first 6 bytes of it is the destination MAC address. So as soon as the switch receives that data, it'll forward the frame, and it is much lower latency, but it's not performing that FCS validation that store and forward gives us. So it may propagate corrupted frames, and this is where you end up with a lot of corrupted data in a network. And then you have your fragment-free method, which is forwards after receiving the first 64 bytes and eliminates collision fragments. So it is a compromise between the cut through and store and forward method, but most commonly in today's networks, we use the store and forward. Um, so can you tell us about switching decisions, Mohammed?
So switching decisions, as we covered before in the MAC learning process, it's like goes hand in hand with that. So the frame processing logic, the incoming frame processing, it goes through, you learn the source MAC address, and then you determine the destination action. So if the destination address is already known, then you send a unicast frame. That means that you already know the destination MAC address and which port to send the traffic to. So you will just send directly to that destination. If you don't know the MAC address of the destination, or the CAM table does not have the MAC address of the destination in the CAM table, then you will send an unknown unicast, which means flood to all ports except the source port, because you already know what the MAC address of the source port is, and that's where you receive the traffic from. So you won't send the traffic back to that port unless, or it will create a loop where you are sending back and forth in your environment. And then you have the broadcast, which also floods to all ports, which is your FF MAC address. And then multicast, you will forward based on the multicast table. And then in the end, you also have port security and VLAN rules, where you could define port security that the specific port only can have that particular device connected, or that particular MAC address on that specific port. If you go into port states, you have forwarding, where you have normal operation. In learning, you are building the MAC table and not forwarding. In listening, you have preparing to participate in the spanning tree, and blocking, you are not forwarding frames. And this goes in line with the spanning tree protocol, where when you connect, which is basically a phenomenon to prevent loops in your network. And that's why whenever you receive from the source, you don't send it back to the source, because whenever you flood the traffic, it's just gonna get a loop. Everybody's just sending traffic back to one another, and that's how the switch makes the decisions.
Yeah, so I think that is a topic that we'll eventually cover in our
Right.
videos, a spanning tree. But essentially, it prevents us from saying, a switch talking with another switch and saying, I have this MAC address, no, I have this MAC address, and basically crashing the entire network just due to a significant amount of broadcast traffic. And with these port states, there's timers associated with them, which we don't mention here, but the blocking essentially is just you're blocking. There's no timer, but as soon as you connect a device to the switch port, it'll listen for 15 seconds. It'll learn for 15 seconds, and then begin forwarding the data. This can be prevented through with a command on the actual interface that is spanning through PortFast, which says, hey, skip those and just go straight to forwarding. But we'll touch more at another video. So let's talk about what collision and broadcast domains are. If you go back and look at our previous videos, we explain in detail what a VLAN is and what a broadcast domain is. But a collision domain, it is essentially when I was talking about duplexes, in a one-lane highway with a two-lane highway, it is a network segment where collisions can occur. Each switch port creates a separate collision domain. It eliminates collisions in full duplex mode. So what does this mean? And I'm not sure if my mouse will be visible to the viewers, but every single connection here, which represents a physical cable in the real world, is a collision domain. So PC0 can send frames to the switch here while also receiving frames. So because it's a two-lane highway, it is able to send and receive, send and receive, send and receive. If for whatever reason it were to negotiate at half duplex, it would not be able to receive while it is sending and vice versa, which is what you see in hubs. A broadcast domain, it is a network segment where broadcast frames reach all devices, single broadcast domains per VLAN, and the switch forwards broadcast to all ports in the same VLAN. So let's assume that PC0 and PC1 are in the same VLAN. If there was a broadcast to be received, to be sent from PC0, that broadcast traffic would get to PC1 and another link that was on the same VLAN on the switch. So an example of this, it is PC1 connected to FA01 or Fast Ethernet 01, PC2 connected to FA02, then a switch, and then FA024, PC3 connected to FA03. And then what you'll see here is that there are 4 collision domains because this is one link, this is another link, this is another link. Then the switch going to the router, that is a 4th collision domain, and then a broadcast domain because we can assume that these are all part of the default VLAN of 1. And if we move on to the next line, Mohammed, do you want to talk about the advanced switch features?
Yeah. So VLANs is one of the advanced switch features. We already covered VLANs in a prior video. But what virtual LANs or VLANs let us do is let us create virtual networks or create logical broadcast domains, which is basically different networks on one switch. And it does through the 802.1q tagging for VLAN identification, and it enables us to do inter-VLAN routing, and which will require a layer 3 device, which if you see the video, or not the video, in the image, the screen capture we have here, that is a layer 3 switch. Spanning tree protocol is also an advanced feature that is available on switches. What it does, it prevents the layer 2 loops, as you mentioned before, and it does through different standards. The legacy would be the 802.1d, the RSTP 802.1w, and we have the latest ones are the 802.1w and then 802.1s. The multiple spanning tree protocol can be used in complex environment where you have multiple switches in one VLAN and you want to enable STP there. As for the port states, you have blocking, listening, learning, and forwarding. As Carlos mentioned, this whole process can take up to 50 seconds or 30 seconds, I believe, in the legacy version. But if you enable port fast on, let's say, the user-facing port, it can be reduced significantly. As for port security, it restricts the MAC addresses per port. So you could tell the switch that if you know that one device is going to connect to one port on the switch, that particular port, you can tell the switch that that port will always have that MAC address associated with that port. And that way you can eliminate other people or unauthorized users connecting their computer by unplugging that PC and getting network access. For the violation actions, like if somebody does that, you could either put the port in protect mode, restrict port, or shutdown mode. If it's in shutdown mode, then as it says, once you connect in, it's gonna shut down the port, and no traffic can be sent or received on that port.
Mhm.
What it does, it also helps with preventing MAC address flooding attacks. So if somebody comes in and plugs into the port, they can do something we call as MAC address flooding attack, and it can prevent that because now you have security enabled, and only one that particular device can connect to that port. You can also do quality of service or QoS, so traffic prioritization and bandwidth management. You could enable that voice traffic has more priority over like your normal traffic. So this will enable you to have smoother experience for like Zoom calls or Teams calls, um, or VoIP calling. And it does through the 802.1p standard, the COS markings, and then it also uses the QI scheduling algorithm. And here in the diagrams, you can see some of the topologies. Like the one at the bottom, it shows that there is multiple switches, and this is the prime example where STP will run because you have three devices and they have links connected. So let's say you forward one of the switches does a broadcast and they're all in the same VLAN. The traffic will just go in loops. It will just flow through between the three switches again and again, again and again. So one of the ports will have to go down for the whole loop to prevent. And STP will do that by default. If you like start a Cisco switch, STP is enabled by default, and that's why it's there to prevent the loops. And again, you can fine tune it to your environment. To again, every environment is different.
Yeah.
But yeah,
No, yeah, if I can add a bit,
yeah,
kind of extend on what you've talked about here, Mohammed, it is when you connect a switch to a switch, which is a very common thing in real world networks, they will immediately exchange something called a BPDU or a bridge protocol data unit, which essentially you'll go into these switches and configure a priority per VLAN. And if they are the same, whatever the lowest MAC address is will win. And we'll extend on what STP is at a later video because it is such an extent topic and so important to know. It can take down entire networks. Um, but what I wanted to talk about was some real world scenarios because all of this theory, you don't know what it means, and it's a headache to understand all these different concepts. So the best way I like to think of port security and where I see it more commonly used is with the sticky MAC addresses that Mohammed was talking about.
yeah,
Because one of my first jobs was at a retail company in the West Coast, and every single point of sale, we would have sticky MAC addresses assigned to it because we don't want a customer going in, disconnecting it, and plugging in something that could hijack our network. So that's where it was primarily used. So it's used to basically prevent anybody going in and plugging in another device. But
right,
it is slowly becoming I want to say maybe an archaic technology with 802.1x now, which
right,
is essentially we'll talk about that, but 802.1x is more commonly referred to now as the port security in switches. But I'll talk about the next slide here. The switch port configuration. So configuring a switch port we did in our last video when we were talking about VLANs. But the negotiation process, it'll when you configure a switch where by default it is auto negotiation, so it'll detect the type of cable you're using, whether it's a Cat5, Cat6, or if it's a fiber or in whatever SFP, it'll auto negotiate that. But in this example, the auto negotiation process, you can either get 10 Mbps, 100 Mbps, or up to a gig, which is 1,000 Mbps. The duplex, whether you get that one highway lane or the secondary highway lane, and then the flow control, which is 802.3x. The port types, which we talked about our last video, you have your access ports, which essentially it gives you that single colored wristband that you can only send broad. You are now part of this color, and you can only talk within that color unless we have SVIs or routing involved. Then you get trunk ports, which is multiple VLANs with 802.1q tagging, which essentially is that hallway that allows all the wristbands to walk through. and then the voice ports. Voice ports, I don't believe we talked about our last video. It is essentially a segregation between your data VLAN and your VoIP VLAN. What happens is it is very common in the real world that you'll have a switch port that you connect to the network. You connect the switch port to a VoIP phone, and then the VoIP phone feeds a computer. So that is a very common topology in the real world. So what you will do from the switch side is differentiate with the switch port access voice VLAN, XYZ, and then just your regular access VLAN for the data. So then you get into port aggregation. What port aggregation is, and I'm sure we'll also do a video on this, is when you are connecting a switch to a router or a switch to a switch, and you only have one link, let's say it's a 1 gig link. One, it is only 1 gig, and two, there's no redundancy associated with that. So if that link were to fail, that's it, your network is down. So what a port aggregation mechanism allows us to do is essentially if I connect now 2 links, so a switch, 2 links, and a switch, I now can aggregate that bandwidth so I can load balance across those links for a total of 2 gigs, and I've also created some fault tolerance in my network. What that means is if link A goes down, link B will now be at half bandwidth, only 1 gig, but it'll still be able to forward traffic. So that is something that is absolutely used in networks today. And the protocols that allows us to do that is LACP or PAGP, or you can just do static with on. It increases bandwidth and provides redundancy, and as we talked about. So if we talk about the switch security features, Mohammed, can you?
Yep. So MAC address filtering, we can whitelist or blacklist specific MAC addresses, and we can add static entries in the CAM table, like we mentioned before. For the port security implementation, we can have maximum MAC addresses per port, or we could have sticky MAC addresses learning. So the first MAC address that is learned on the port, it's gonna stick with that. If another person comes in and plugs another device into that same port, it's gonna say, no, you can't do that. And it's either gonna, whatever you set the violation response to, it's gonna do that. You could just say shut down, and it's gonna shut down that port if another device comes and plugs in. You could also configure DHCP snooping, so it validates the DHCP messages. It builds the trusted/untrusted port database, and it prevents the rogue DHCP servers. And also you can configure dynamic ARP inspection, which will validate the ARP packets against the DHCP snooping database, and it will prevent ARP snooping attacks. But yeah.
Okay, cool. So I think for the next portion of this video, when we're talking about switches, it is very there isn't a lot of labbing you can do to truly understand a switch. It's more so the theory and the concepts associated with it. But Mohammed has taken some time and prepared a lab to kind of demonstrate what a MAC address table looks like, what it does when you connect an endpoint to it and assign a VLAN.
So here we have our lab topology. We have a layer 3 switch right here. We don't really need this router, so I'm going to just delete that from our lab. But yeah, so we have a layer 3 switch. The layer 3 switch is running multiple VLANs. So if we do, first of all, go into privilege exec mode and do show VLAN brief. We should see here we have 2 VLANs, VLAN 10 and VLAN 20. And VLAN 10 has port 10 associated with it. So we can see here fast Ethernet 10, which has this particular PC, which is PC number 7 in that VLAN. And we also have VLAN 20, which is the IT VLAN, and it has 2 ports in there, fast Ethernet 1, which is this one, and then fast Ethernet 2, which I believe is this one. Yeah, 0, 1, and 0, 2, my bad. Now that we have that, right now, nobody's communicating to anybody else. So like no PCs are communicating to each other. So there is no traffic on the network, and there shouldn't be any MAC addresses either or in the CAM table of the switch. And we can check that using the show MAC address table command. And we can see here there is nothing in the CAM table right now, MAC address table right now. What we can do now to initiate some traffic, we can try to ping from PC 0 to PC 1. So let me go to PC0 here. And let's ping PC1. So which will be 10.10.10.200. If we do that, 10.10.200. I can see my ping is successful here. I'm getting response back. And now if I check the MAC address table again, I will see here that I'm learning the MAC addresses from the devices. And I can see the VLAN first of all, the VLAN 20, because these two devices are in VLAN 20 as we covered that before. I see the MAC address and I see the source. I see the source MAC address and I see the port as well. So this is ending in 9459. So if I do ipconfig/all, I should see here, this one is A8AE, which is this one, A8AE, which is fast Ethernet 0/1, and this is PC0. So PC0 MAC address,
I
and
believe it's wrong
oh
on the
yeah,
actual topology. Yeah, but
I,
that's no big deal.
I think so, yeah. But this is the source MAC address and this is the port that it's associated with.
Yeah.
And here
Mohammed, if
we
you
covered
want
that.
to, I think it's good that we if you want to issue the show interface FA01 or 02 command, so we can see what the negotiation looks like from a switch standpoint.
Yeah. So now that we
Yeah.
see the details about the port, we can see
So
the
I think
MTU.
it's very important for people to understand what this command really means,
Right.
right? Because I've used it about 1,000 million times to troubleshoot things. So first of all, and if you let me kind of talk about what this means, is all right, let's see what the MAC address is of my switch port. What you'll notice in a switch is that every single port has its own unique MAC address simply because the computer needs to be aware of the MAC address it's also going to communicate to.
Right.
Every single computer, when it's sending frames, is going to have a destination MAC address unique to the switch port they are connected to. And that's the first thing I'll notice. Then I'll see the MTU. The
Yep.
MTU on that port is 1,500 bytes. So that's what the maximum size that the window size accepted by that switch port. And that's where you'll run into jumbo frames and all that.
Yeah.
Um, my bandwidth is what is that? Kilobits. Okay, so that is 100
Yeah.
100 Mbps. My delay is 1,000 USECs. My reliability is 255, and my load is 1 out of 255. So
Mhm.
then what I'll really focus on is the duplex part. You'll notice that it negotiated at full duplex at 100 megs.
Yeah.
And that is good because we can take advantage of that two-lane highway that we talked about. And then that bottom part where it says the input and output rate. So this is extremely important when troubleshooting things. You'll see that there is an input and output. So in the real world, you run into things where, so the server people will tell you, why is my server not going out in the network? Something's wrong with your network. But actually, the whole time, their server's not trying to send any data. And that
Right.
is a very common thing. They gotta reboot their server, and then things are back to normal. So then I'll also go with the CRCs. You'll see the input errors. What that means is imagine this is the interface. Incoming to that interface,
Mhm.
how many CRCs are there? Remember when we were talking about the the validation that the switch does?
Mm.
So that's where that comes in. The CRCs, the frames, the overruns. What is that? Is there any errors incoming to the interface? Then the collisions, is it maybe negotiating at health duplex at times? Is there any collisions? Is there any bubbles? Is there any carriers, lost carriers, or buffer failures, and so on? So this commit is extremely important when you're troubleshooting things because it can point to a potentially bad cable, a bad SFP, something wrong with the NIC of a server. It is such a simple command that can give you so much information.
Right.
So sorry I stopped you there,
No,
Mohammed.
no, this was great information. Now that we have seen that how the switch learns the MAC addresses of the source ports and the destination ports, here we can see it already learned. Next time it already, yeah, I don't know if he, so Carlos, is there any other command I can use here for like MAC addresses?
No, not
Yeah.
not because no, that's it. Just the show MAC
Yeah.
address. You can do the show VLAN brief. It will tell you the ports
Yeah.
assigned to that VLAN. So you'll see if A01 and 02 are there. But
Yeah.
so let's ask the question, Mohammed. Why is your why is PC7 on your bottom left not showing in your cam table?
It hasn't communicated to anything yet, so there is no traffic coming from it. So that's why we don't see anything
Right. And I
in
remember
the
when we were setting up this lab earlier in the call, we did verify that it was. So what essentially is happening, that timeout of five
right.
minutes has occurred since we started this video, and you would need to basically generate some traffic to that computer in order for you to see it in the cam table. So maybe from the switch, do you want to try pinging it to see if it just
Yes. Let
magically
me
appears in the cam table?
try to ping it. So it's 10.100 or 100 or 100,
Mhm.
and all the pings are successful. So we can
You should
do.
see it in the cam table now, yeah.
I can see VLAN 10 in here,
Yeah, right.
and that is the device because that is on
That is
VLAN
the
10.
device. And then time has passed, and now the VLAN 20 MAC address table disappeared.
Yep.
So that's
Yeah,
that's
this is a lab
unfortunate.
environment, so it's not like a real switch. The real switch will probably have more bigger
Yeah,
timeout.
yeah. Well,
So
I'm
it
sure it's been
will be
more
quick.
than 5 minutes since I went on about
Yeah,
what
that is also true. Yeah.
but yeah. But no, that is great. I think for the purpose of the video, I think that is enough about what a switch is. Obviously, we can go in so much detail, but in so little time. Um,
Right.
we'll talk. This is a very high level overview. If anybody has any questions or any details, just please comment, and
Yeah.
Mohammed or I will be happy to help.
Yeah.
Uh, and we also have attached our LinkedIn profiles to the YouTube channel, so feel free to reach out through there. Um, yeah, I think that's it. That
Yeah, I
concludes.
think this covers what a switch is and what its role is in a LAN, what our
Yeah,
topic was, because you can see here what a switch is
yeah.
doing. It's
Well, yeah.
storing.
And I think it's also good that we talk about the real life aspect of what a switch is, right?
Right.
So a switch in the real world composes of you get these examples of one, you get your data center switches, which are doing protocols that need to be very high speed, very redundant, very expensive. And then
Right.
you get your end user facing switches, which let's say you work at a school that you need to feed all those different classrooms and different computer rooms, or maybe you're at Disney World and you have 1,000, well, hundreds of thousands more than likely access points that you need those switches to be feeding those access points. So they're very cost dependent. There's extremely expensive switches. There's very cheap switches that do just fine for what you need it to do. Um, Another concept that we didn't really talk about is also stacking switches. So
Yeah.
what stacking switches means is if I have two 24 port switches, if I have two 24 port switches and they are the same, model, what I can do is I can go into, depending on the vendor, but on a Cisco switch, I can go and connect the back of it with stack cables, we call them. And what that'll do is it'll create a logical single switch with two
Right.
different switches. So now I have one management IP address that I need to manage that I can access, and it'll essentially think that every switch is a different line card. So you'll
Yeah.
have like your ports will be 101 for switch one, then 201 for switch two. I don't know if you have anything else, Mohammed, but
Yeah, I want to just show one more
yeah,
last thing
of
before
course.
we there is this simulation thingy in this lab environment.
Yeah.
Um, if
Send it to that MAC address.
yeah, it's like a feature of this.
Yeah, the
Right
packet
now,
tracing.
yeah, let me just stop it because I don't know what it's doing mostly because I had too many filters on. Maybe in the next lab we'll show more of the simulation part. But yeah, this is a very powerful tool, the
Yeah.
simulation part.
Yeah.
But yeah, I think this covers most of the what the switch is and what the LAN
Yeah.
what the role in LAN is of the switch.
Okay, awesome. Well, I hope this video is useful to you guys, and we'll talk on the next one.
Yep.